The pH is 2, absolutely. So what is then, if the pH is 2, what is the concentration of HCl? I'm going to pause here just for a second, see if you guys can get it. Yeah, 10 to the negative pH, right? And so that's going to equal, because it's a strong acid, that's going to equal our hydrogen ion concentration. Okay, let's see, HCl, H plus, what am I looking for? Right, 10 to the negative pH. Okay, so if you needed to figure out the initial concentration of the H plus, that is how you would do it. Excellent. All right, I'm gonna make this smaller so you can see everything on one screen. Okay, it might be a little bit tiny for you, but do the best you can. What volume, so this titration curve here, I'm just gonna zoom in on the bottom part. This is the titration of a strong acid with a strong base. It is the titration of 50 milliliters of 0.1 molar solution of hydrochloric acid. Okay, with 0.1 molar NaOH. All right, so I'm going to write that up near the curve. Okay, so up here we have 50 milliliters of 0.1 molar HCl, and it is titrated with 0.1 molar NaOH. And the question that is being asked is, what volume of NaOH would be needed to reach the equivalence point if the concentration of the added base were 0.2 molar? Okay. So when the concentration of base was 0.1 molar, it took 50 milliliters to reach the equivalence point. What volume would it take to reach the equivalence point if instead we now had 0.200 molar NaOH? See if you can figure that one out. What have I done to the molarity of the NaOH? I started with 0.1 molar, and now it's 0.2 molar. If I double the concentration, it's going to take half the volume. So our curve with the 0.2 molar NaOH would look exactly the same, except that this vertical section would occur at the 25 milliliter mark. Okay, there we go. Something like that. Okay, very good. Why is it half as much? Because we doubled the concentration. Okay, let's carry on here. All right, Now instead of titrating hydrochloric acid, we are now titrating acetic acid. What is the difference between acetic acid and hydrochloric acid? What kinds of acids do we have? Yeah, acetic acid is weak, absolutely. Okay, so before we answer the questions up there, let's focus on what are the differences in the titration curve. Okay, we did this last day. See if you can name 3 differences in the titration curve. You might even be able to do 4, but let's try for 3. And my chat keeps disappearing on me. I'm not quite sure why, but that's okay. Can you think of any differences in this curve from the one on the previous page, the strong, strong? Yes, we have that little hill at the start. Oh, I need to do that and do that. There we go. Okay, so the number 1, there's a little hill at the start. Number 2, let's see, number 2. The equivalence point is greater than 7. And yeah, we have a shallow slope, although we still get a shallow slope in the strong, strong as well. So if we just scroll back here, you can see we have a shallow slope at the beginning. We have a shallow slope at the end, but take a look at that vertical portion of the curve, right? In the strong, strong, it is very long, but in the weak, strong, it is much less tall, okay? So a third difference is that the vertical section vertical section is shorter. Okay. And there is actually one more. Let's see, can anyone think what that would be? The initial pH is higher, okay? At a 0.1 molar concentration, the pH of acetic acid will be the pH will be higher, the hydrogen ion concentration will be lower. So number 4, the initial pH is higher. Okay, so down below, there's a little picture of what's happening at each portion of this curve. Okay, and you can see that initially we have all CH3 COOH, and it's not dissociated, okay, because it's weak, it's almost all together. As we get halfway, and this is going to become important, that halfway point on the curve, you have reacted some of the CH3COOH with hydroxide. Okay, what does that reaction look like? CH3COOH plus OH minus. We're just going to do the net ionic here. I'm going to leave out the sodium. That's a spectator ion. Okay. Is this a one-way or a two-way arrow when we have that neutralization there? Is that a one-way arrow or a two-way arrow? Okay, remember that we are dealing with the OH is coming from NaOH. And what type of a base is NaOH? It is strong. And if it is strong, it's going to drive that reaction to completion. So what's really going to happen is the OH minus is going to rip the hydrogen ions off of the acetic acid. It doesn't matter that the acetic acid is weak. Okay. Because the OH is strong, the OH rips the protons off. It doesn't have to wait for them to dissociate. Let's see, it doesn't matter that the acetic acid is weak, the strong base rips the protons off the weak acid. It doesn't have to wait for them to dissociate. And if anyone's like, oh my gosh, I wish I could write this down on the piece of paper, it's okay. I will post the PDF of this file, okay? So you can have that for reference for yourself. Let's see, the base rips off the weak acid. It doesn't have to wait for weak acid to dissociate. Okay, so as long as you have one strong thing in your reaction, the reaction is going to go to completion and it is going to be a one-way arrow. And that is something that most students forget most of the time. Okay, so be sure that you remember this is hugely important. Okay, all right. So, that being said, what's going to happen is, there we are. Okay. So what's going to happen is we are going to, what am I saying? Right. Halfway through the titration, we will have reacted half of our reactants. So we will still have some CH3 COOH left. Okay. We have half of our CH3 COOH. Half of it has been reacted. We also have an H2O, another H2O, which is not shown here. Okay, the NaOH, the OH, and one of the H's has formed H2O, and now half of it has been turned into acetate. Okay, so we have two things in our solution right now. We have two things that matter. Okay, yeah, we have our sodium ions, but we also have the acid, and we have its conjugate base. So half of it is still unreacted in its acid form, and half of it has had its protons ripped off and has turned into its conjugate base. If that is the case, what kind of a solution do we have if we have half acid and half conjugate base? Yes, that's a buffer. Absolutely. And so it's important that this region here, just around the halfway point, okay, this is called the buffer region. And the closer you are to exactly at the halfway point, the better of a buffer it is. Okay. And we call that point the 1/2 equivalence point. So at the 1/2 equivalence point, you have 1/2 unreacted acid, and you have 1/2 has been turned into the conjugate base. And so if you have the acid and if you have the conjugate base 1/2 and 1/2, then that is a buffer. Okay, excellent. Okay, let's see what else we have here. If the acetic acid being titrated here were replaced by hydrochloric acid, okay, so we have acetic acid in this thing and it is 0.100 molar. Let's say we replaced it with hydrochloric acid also at 0.100 molar. Would the amount of base needed to reach the equivalence point change? So we're comparing 0.1 molar acetic acid versus 0.1 molar HCl. Would the amount of base needed to reach the equivalence point be the same, or would it be different? Anyone else want to weigh in? No, everybody else is chicken. Thank you, Deborah and Maya. Okay, yeah, it will actually be the same because it doesn't matter in our equation. Remember, both of them go to completion. If I was to have here HCl instead of CH3COO minus, it is still a 1-to-1 ratio to get the same number of moles, and so it will still be the same volume to get that same number of moles. Okay, and I realize that I've written all over this page in a crazy fashion, and you can probably hardly even follow that, but that's okay. Okay, would the pH at the equivalence point change if we changed from our 0.1 molar acetic acid into the 0.1 molar HCl? Would the pH at the equivalence point change? Yes. Would it be higher or lower? And if you want to, if you actually know the value, If we change it to 0.1 molar HCl, you can let me know that. Yeah, it is going to be pH 7. Okay. If we had HCl plus NaOH gives NaCl plus H2O. Remember, at the equivalence point, we have used up all our reactant and all we have left is product. And our product is a salt and water. And when we have a salt, what do we have to check for? Yeah, we have to check for hydrolysis. And so we say, does Na plus hydrolyze? And the answer is no. Does Cl minus hydrolyze? And the answer is no. And if there is no hydrolysis, then your pH is going to be 7. Okay. But remember, if we had our original solution, we ended up making CH3COO minus, and CH3COO minus, will it hydrolyze? Yes. Okay. You would end up with CH3COO minus plus water forms CH3COOH plus OH minus. And therefore, our pH would be, we have made hydroxide, therefore the pH is greater than 7 at the equivalence point for that weak strong. Okay. Whew. All right. How does the pH at the equivalence point change as the acid being titrated? So we're looking here now. As the acid being titrated becomes weaker, what happens to the pH at the equivalence point? So how does the pH at the equivalence point change as the acid being titrated becomes weaker? Well, we can look at these curves here and we can say we go from 10 to the negative 2 as our Ka. That's a fairly strong weak acid, all the way down to a Ka of 10 to the negative 8. And you'll notice that the pH at the equivalence point gets higher and higher and higher as the acid gets weaker and weaker and weaker. As the acids, it would be different acids, get weaker, the pH at the equivalence point gets higher. Why is that? Well, as your acid gets weaker, let's call this HA1, and let's call this HA2. Okay, we're just going to compare our strongest weak acid with our weakest weak acid. as the acids get stronger, what happens to their conjugate bases? Yeah, they get weaker. And remember, the product of neutralization is a salt that contains the conjugate base. So if we had, if we had NaOH, here's 3 examples, plus HCl, that's going to go to NaCl plus H2O. Our ion, our conjugate base, is Cl minus, and it is such a weak base that it cannot hydrolyze. If we have NaOH plus HA1, which is the stronger of the 2 weak acids, remember this is a one-way arrow because the NaOH is strong. Okay, we end up with Na A1. So our anion here is the A1 anion. That is our conjugate base. And because HA was the stronger weak acid, its conjugate base is going to be relatively weak. Okay, and so it is going to produce less OH minus than A2 minus, which I've run out of room to write the reaction for, which is a stronger base, which is a stronger base. Okay, so if we had NaOH plus HA2, this is a weaker acid. We would end up with NaA2, which contains the A2 minus ion, which is a stronger weak base, and therefore it will produce more OH minus than A1 minus. I'm starting to realize I need to leave a lot more space in these documents. Ha! Oh well, that's okay. Next time. Any questions? Oh, okay. So now we're going to look at, we're going to titrate a weak base with a strong acid. So in our flask, we have a weak base, and in our burette, we have our strong acid. Okay. And because we've got a weak base, the pH, if we had had a strong acid, let's say we had Oh, never mind. That's a question that goes on later on. Here is our initial pH, and it's high because we have a base. Okay, we start adding acid and the pH goes down and the pH goes down and the pH goes down. And then at the half equivalence point, remember we have converted in our reaction that would look like this, NH3 plus HCl goes to NH4 plus Cl minus. And remember that HCl is strong, and as long as you have one partner in the neutralization that is strong, it will go to completion. Okay, so halfway to the equivalence point, so at the half equivalence point, we have 1/2, which is NH3, and we have 1/2 that has been unreacted. So at the 1/2 equivalence point, we have 1/2 of the NH3, which has been unreacted. And at halfway to the equivalence point, we have 1/2 has been converted into the conjugate acid. So we have 1/2, which is unreacted weak base, and we have 1/2, which is the conjugate acid. And so that means that we have a buffer. So this would be the buffer region, is close to the equivalence point or the half equivalence point. Okay. Some questions. All right. So, and we look at the equivalence point. There's probably a question down below. Yeah, okay, there is. So, what would the initial pH be if the base in the flask were 0.1 molar NaOH instead of 0.1 molar NH3? So, what if we had a strong base in there instead? Sorry, I'm just going crazy here. There we go. The initial pH would be slightly higher. Yes, it would definitely be higher because NaOH is a strong base. And NH3 is a weak base. Can you calculate the exact pH that it would be? Well, we know our concentration of OH. (0.1 molar, which is the same as 10 to the negative 1 molar. Therefore, our pOH is going to be 1, and therefore our pH is going to be 13. Yeah, excellent. Okay, so you can see If it was NaOH instead, it would be there, okay? But it's not, it is a weak base. Okay, what is the initial, why is the initial pH of the NH3 lower than the initial pH of an NaOH solution of the same concentration? I think that's fairly straightforward because this one is weak, therefore it produces, less OH minus per mole of base. Write the reaction representing the neutralization of NH3 by HCl. We did that, didn't we? Yes, we did. It's right up there. So I'll just write it down here. NH3 plus HCl gives NH4 plus Cl minus. And so when we've reached the equivalence point, who are the only species present? Nobody? At the equivalence point, all the reactants have reacted. So these guys are all gone. Okay, so the only things that we are left with then is the NH4 plus and the Cl minus. And so our salt would actually be NH4 Cl if we wanted to write it together. So who are the ions? We have NH4 plus and we have Cl minus. Does NH4 plus hydrolyze? Yes, it is one of those four along with feel creepy. Chloride does not because its conjugate acid is strong, HCl. Okay, and so you guys are going to now try for yourselves to write the hydrolysis equation and decide whether the solution is acidic, basic, or neutral. So try that for yourself. And then when you're done, you can just write done. Okay, NH4 plus is an acid, so it will donate its proton to water. And we will end up with NH3 plus H3O plus. Is our resulting solution acidic, basic, or neutral? Absolutely, yes. We have made H3O plus, and therefore the solution is acidic. And we can see that because at our equivalence point, we've got our NH4, it hydrolyzes and makes H3O plus, and that gives us our equivalence point, which is less than 7. And why is that? That is due to the hydrolysis of the salt, and in this case, the cation. Okay. All right. That has been a 45-minute lesson. Do you feel like we are good at this point? And we want to pause for another day, or do you want to keep going? What would you like? Pause. Excellent. Good. I feel that way too. All right. Only 2 people voted, but we're going to pause regardless. Okay. So, just a couple of things. Number 1, next week, or actually number 1, you guys have a hydrolysis quiz, which is the only sort of homework that you're working on at this point. I have posted an assignment about the titration worksheet, but just ignore it because we haven't finished the titration worksheet yet, so I will unpost it. So the hydrolysis quiz, it says that it is due on April 17th, which is 2 days from now. However, if it comes in a little bit later, I'm okay with that. It's not really a big deal. I'm also going to scan in your KB quizzes so you can take a look at them because some of it is related concepts. I'll scan your KB quiz so you can see it or take a picture or something. Okay. The second thing is next week. Let